So properties of parallelograms. Let's think about so parallelogram is one. It's a quadrilateral, right? Does everybody have a packet? So it's a quadrilateral. But what's special about this quadrilateral? So it's a quadrilateral with two pairs of parallel sides. So it's a special quadrilateral. It's got two pairs of parallel sides. Squares and rectangles and rhombuses would all fall into that category, which is what we're studying next. So we're kind of starting big with just quadrilaterals, going a little smaller to parallelograms. Not all four-sided shapes are parallelograms. And then from parallelograms, we'll go and talk about rectangles, squares, and rhombuses, because they're all parallelograms. But they have even more specificity here. So that's the definition of a parallelogram. The next four theorems are true if you establish that it's a parallelogram. So quadrilateral is a parallelogram. If it is, then its opposite sides are congruent. So the two pairs of parallel sides, if you break the parallelogram into two triangles, like this one over here, you can actually prove ultimately using congruent triangles and CP, that the opposite sides are congruent. Okay, you'll get a chance to do that later. The opposite angles are congruent. So with these angles here and here, and then these angles here and here are congruent. Opposite sides are not only parallel but congruent, so you can mark it like that. Consecutive angles are supplementary, so these two guys here and here add up to 180. And if a quadrilateral is a parallelogram, then the diagonals bisect each other. So these diagonals inside bisect each other, meaning it splits these into, I'll highlight them here. These two pieces are congruent here and here. And then these two pieces are congruent here and here. So those are theorems that can be proven about parallelograms. But the definition is just it's a quadrilateral with two pairs of parallel sides. That's the definition. And these are all true theorems about parallelograms. So we're going to be asked to find missing lengths within parallelograms. Let's see if we can do that. We're given that FG is 23. So what's JH if it's the opposite side in parallelogram? Okay. FG is 23. Here's FG right here. What's this JH got to be? Also 23. And JK, where's JK here? So JK is half of this guy right here. So JK would have to be 16 as well. So JK is 16. So JH is 23, and then GH looks like it's opposite FJ over there. So GH is going to be 19 because opposite sides of a parallelogram are not only parallel but congruent. Because of the share a side case, you see this guy right here? I'll show you. This triangle right here and this triangle right here, they have to be congruent. I'm trying to use every color today. But those two have to be congruent by side, side, side because of the share side case that makes them congruent. And because they're congruent, the opposite sides. Congruent here, we can prove those theorems based on what we do know. Actually, you could use alternate interior angles are congruent, and then share a side, so you get angle, side, angle, and then you can prove the sides are congruent. All right, find the angles in the parallelogram. So we're going to use the angle theorems. So here's a parallelogram. We're going to find measure of angle A. Measure of angle A is opposite this 78-degree angle. So that means measure of angle A is 78 degrees. Yeah, measure of angle A is 78 degrees. And angle B, a couple different ways you could go about getting angle B. If you could figure out angle D, you could set angle B equal to angle D. There was a fourth theorem in there at the very bottom that said consecutive angles are always supplementary in the parallelogram. So we're going to use that one. It's a little more direct. So 3x plus 78 has to equal 180 degrees. And then solve that for x. So subtract 78. So 3x equals 2. And then divide by 3. So x equals, goes into 10 3 times, into 12 4 times. X equals 34. So if x equals 34, 3 times 34 will give me 90 and 12. 102. I could have stopped right here. So 3x equals 102. Could have just solved for 3x, it would have been done. But we need to find x anyway. So x equals 34 down here. X equals 34. So opposite sides are congruent. The diagonals split each other into equal halves. Opposite angles here are congruent, here or here. Consecutive angles, like the ones I circled, are supplementary. Those are the 4 theorems that tell you things about parallelograms. So that means those are true for rectangles as well, and squares, and rhombuses. They're all categorized as parallelograms. All right, so the parallelogram is drawn, the first quadrant is shown. What are the coordinates of vertex C? So how can we figure out vertex C? Well, here we have, this is Z, from here to here is Z. That's the distance of Z. From here to here, let's draw it. See that little red piece right there? That's the same distance that B is horizontally away from there. So I could call that red piece x here, and I could call it x right here. So I've got an x coordinate for C that is z plus x, comma something. How high up am I at C? Y. Y, yeah, it's this guy right here is y. So that's a coordinate because the amount it shifted over here is the same amount it shifted over here. It's like taking a rectangle and tilting it, but you tilt it the same distance on each side. As a matter of fact, the area formula for a parallelogram, believe it or not, is the same as it is for a rectangle. Because I could take this little piece right here, cut it off, and move it, slide it in over here, and I have a rectangle anyways. Right? So they have the same area formula. So for that reason, that coordinate is just z plus x, where x represents the part you come over from the vertical line or the y-axis. Find the value of x, y, and z in the parallelogram. So here we have a parallelogram, all kinds of variables in here. We know opposite angles are congruent, and we know consecutive angles are supplementary. Now here's the problem if I set up an equation with consecutive angles. If I set up these two down here, here and here, I have 2 different variables, right? That's not going to help. Same thing here and here, here and here, or there and there. So I don't probably want to use consecutive angles first like I did in the last one. But I do know that opposite angles are congruent. So I'm looking at those 2 opposite angles that have x's in them, right? And I'm going to set 3x minus 18 equal to 2x plus 12. So set those 2 equal. And then solve for x. So subtract 2x from each side. So x minus 18 equals 12. And then add 18 over. So x equals 30. So I've got x is equal to 30. So I'm probably going to need to find this angle here. So it's 2 times 30 plus 12, which gives me an angle measurement at 72 degrees, which tells me that 3z has to equal 108. It's 180 minus 72. And it also tells me that 4y equals 108 as well. So That's how I get the other two variables. So divide by 3 here. So z equals 36. And divide by 4. We've got y equals, goes twice, and 28. So I've got 27, 36, and 30. So they have a lot of use the theorems or the definition of a parallelogram to set up an equation and solve for a variable. And then they might ask you to go back in and plug the variable in to get the degree measure. Okay. But remember, as you go around, this is the first lesson, what do all these angles have to add up to? That might be helpful as well. 360. So we got a little proof to do here. It says given ABCD is a parallelogram. We want to prove AB is congruent to CD. Oh, that's the first theorem there. And BC is congruent to DA. So we're going to prove that those two are congruent using one of our ASA, SSS, that type of stuff. So here's what it looks like. One, we're given that ABCD is a parallelogram. That's given. Since this is a parallelogram, we've got a couple pairs of parallel sides by definition of a parallelogram. And so therefore, we can state some angles that are congruent by alternate interior angles. For example, I've got angle 2 is congruent to angle 3. See those two alternate interior angles. Then I've got another set, right? Angle 1 is congruent to angle 4. That's by alternate interior angles theorem. So I've got a set of angles here congruent, another set here congruent. So I've got a couple of angles in each one of those. And then we've got the share aside case. So AC is congruent to AC by reflexive property. That's congruent to itself by reflexive. And then 4, we've got a couple triangles that are congruent now. We could say angle or triangle. ABC is congruent to triangle CDA by angle side angle. Once we prove the triangles are congruent, we can then use CP-CTC to prove the sides are congruent. So I've got AB is congruent to CD, and BC is congruent to DA by CP-CTC. And so that's the first of those theorems that we gave you at the beginning of this lesson. So parallelograms have opposite sides congruent, opposite angles congruent, consecutive angles are supplementary. And I combined 6-3 with this, so we're going to look at 6-3. It's all related to parallelograms. So. All right. So some more theorems here. Give us 5 more of them. If both pairs of opposite sides of a quadrilateral are congruent, then it's a parallelogram. So if both pairs of opposite sides are marked as congruent, not necessarily parallel, but congruent, then you can prove that it's a parallelogram. If an angle of a quadrilateral is supplementary to both of its consecutive angles, then it's a parallelogram. If both pairs of opposite angles of a quadrilateral are congruent, typo there, just say are congruent, then it's a parallelogram. If the diagonals of a quadrilateral bisect each other, then it's a parallelogram. And then if one pair of opposite sides of a quadrilateral is congruent and parallel, then it's a parallelogram. So 4 of those are the converse of the theorems from the other section, okay? So we can make them into biconditionals. So if any of those properties that we looked at in the first section are true, then it's a quadrilateral. So it says decide, if you're given enough info, to tell that the quadrilateral is a parallelogram. Explain your reasoning. So we're not writing a full proof, just explaining our reasoning. So A, you might have to look over that list. It's one of the ones that is not a converse from the first section. But it says if one pair of opposite sides of a quadrilateral are congruent and also parallel, that's enough to prove that it's a parallelogram. So look at A. I don't know if you can see it here. You've got the hash marks, means they're congruent. See the little arrows on there next to it? Kind of funky looking arrows, but congruent and parallel. So that means by theorem 612, this is a parallelogram. We don't want to say theorem 612 because that numbering system is not necessarily universal, but we'll say because opposite side are congruent and parallel. You can do it with shorthand. So opposite sides are congruent and parallel. So that's a parallelogram. What about B? Does it fit any of those 5 theorems up above? Yep. So Grayson is saying since both pairs, oops, that's not going to work. Okay. Can't do that. Right. That might let me. Okay, so both pairs of opposite sides are congruent. So you don't have to do a full proof. You're just identifying which of those properties are being exhibited there. I should have done D right after A. How does D differ from A? It's got a pair of congruent sides. It's got a pair of parallel sides. But it's not a parallelogram for one reason here. You see how it differs from A? Okay, not in the same way, so you're on the right track. It's marked a little differently. It's got the same markings, they're just on different pieces, right? It's got opposite sides congruent and opposite sides parallel. So D is slightly different than A. It's not necessarily a parallelogram. So all these look like parallelograms. They're going to, that's always the case. But you have to be able to prove they're parallelograms based on the marking. So D is actually not a parallelogram. So D is not a parallelogram. It says if one pair of opposite sides of a quadrilateral are congruent and parallel, it's got to be the same sides that are congruent and parallel, and this is not. Unless it fits one of the other ones up above. Do the diagonals bisect each other? No. What else do we have up here? Are the opposite angles congruent? No. Do they have supplementary consecutive angles? No. Both pairs of opposite angles are congruent? No. So D is not a parallelogram. It's just slightly different than A. So just be aware of that. It's like the one that has the same things. It has opposite sides that are congruent and then opposite sides that are parallel, but they aren't the same. What about C? What's given there? It's just a picture. I don't see any markings. Do you have any markings here? Okay. So we have angles that are congruent here. So here and here, and then here and here.
So it would be 610.
So what's that?
It would be 610.
610? What does 610 say?
There's opposite angles equals
Could be a parallelogram. You're right. You're right. The other way you could prove it is actually the same way we just did that. proof from the previous section. This would be angle side angle congruence. So you'd have the triangles congruent, so you could actually prove the opposite sides are congruent. That would be another way to explain it. But you're right, I believe it is 610. It says, now, it says both pairs of opposite angles have to be congruent. If you put these two together and these two, I would agree those are congruent. How would you prove that these angles here and here are also congruent? Any ideas? This little obscure theorem that we had a couple chapters ago. If two angles in one triangle are congruent to two angles in the other, what's true about the third angles? What's that? Yeah, the missing piece, the missing angles, or whatever we call it, the third angles theorem, have to be congruent too. So you could prove it in that way as well. So you could say the third angles, or these, have to be congruent as well. But ultimately, this is a parallelogram, and you're right. You're right, it is 610. So parallelogram, opposite angles are congruent. And if you're doing a proof, you would have to demonstrate to me that either, well, there are a couple ways you could go about it. You could say by the third angles theorem, these opposite angles are congruent, and then you have both sets of opposite angles congruent. Or prove the triangles are congruent by ASA, therefore the opposite sides are congruent by CP, CTC, and you can say it's congruent by, I think, theorem 6H. What about E? I think I saw it up here. E looks like 6.9. If an angle of a quadrilateral is supplementary to both of its consecutive angles, then it's a parallelogram. So see this angle? It's supplementary to that guy and that guy. So since 120 degrees, this is a parallelogram. 120 degrees is supplementary to both of its consecutive angles. There it is. As you're going through this assignment, you have to have that sitting in front of you probably. This last one on here, I don't have any instructions. It looks like yours does. What would x have to be to make this into a parallelogram? Is what it asks, right? Find the value of x to make shape parallelogram. So find the value of x. So, well, to be a parallelogram, if this is 4x, this would have to be 4x over here, right? Opposite sides have to be congruent. And what do those have to add up to? 360 over here. So we've got 4, 8, 9, 10, right? 10x equals 360, because all those have to add up to 360. So divide by 10, x equals 36. So if x is 36, we got a 36-degree angle here, 36-degree angle here, and 144-degree angles here and here. And opposite angles congruent gives us a parallelogram. So this is a little precursor example to of what's to come at the end of the unit, kind of combining coordinate geometry, algebra and geometry, I guess. A little bit of maybe Pythagorean theorem and finding distances and finding slopes, comparing slopes. But we got to determine or prove that those four vertices give us a parallelogram. So different ways we could do it. We could use one of these theorems from this section, or we could prove that the opposite sides are parallel would work. Go right back to the definition. So let's go ahead and draw this four-sided figure and see if we can prove it. So we got 2, -1 right here. That's A, and then we've got 1, 3 is up here. So just plot these points with me. 6, 5. and then 7, 1. So it goes A, B, C, D, connect the dots. Kind of looks like a parallelogram. So there are different ways you could go about proving this is a parallelogram. You could use the distance formula and prove that AB is congruent to CD and BC is congruent to AB. That would be one way to do it, the distance formula. Can't do anything with the angles. Anything with the angles because we need a protractor to measure the angles. You could look at slopes of BC and AD and prove that the slopes are the same there, and the slopes of AB and CD are the same. Because if you have two pairs of parallel sides or same slopes, then it's got to be a parallelogram. So you have a couple different ways you could do this. Just for practice, because see, the previous section was the definition of a parallelogram. So that's when we proved the opposite sides are parallel. This one we have a theorem, 6-8, that says if the opposite sides are the same length, then it's a parallelogram. So I'm going to do a little review of the Pythagorean theorem in this one. So we'll do it that way. So here's how this works. Going from B to C, I go up 2 and over 1, 2, 3, 4, 5. So let's say BC is equal to the square root of 2 squared plus 5 squared, or square root of 29. So what I want to do is prove BC is congruent to AB. Okay? 1, 2, 3, 4, 5, and then 1, 2. So I already know AB is equal to the same thing, square root of 2 squared plus 5 squared, which equals square root of 29. Now let's look at these two sides. AB is 1 over 1, 2, 3, 4. So length AB is equal to square root of 1 squared plus 4 squared, which is equal to square root of 17. CD is 1 over 1, 2, 3, 4. So CD is equal to square root of 1 squared plus 4 squared, which equals square root of 17. So you just find those 4 lengths using the Pythagorean theorem over and over again. Okay? And then you need to make some statement that ties all this together. So since opposite sides are congruent, A, B, C, D is a parallelogram. That's the example. That's an example of a coordinate-related proof that a shape is a parallelogram. And we're going to do that for other shapes, for squares, for rectangles, for rhombuses, rhombi, however you want to say it. Do it. We may even do it for a kite or for an isosceles trapezoid. But any of these quadrilaterals, you can prove which type it is based on like distances, lengths of sides, or on the fact that opposite sides are parallel, things like that. Get all that written down.